Today, we are going on a journey. We're going to uncover the simple, almost elegant rules that, believe it or not, govern how we see absolutely everything around us. We're pulling back the curtain on the secret life of light. Have you ever wondered about this stuff? These little everyday optical illusions? Well, the answer comes down to two core ideas: reflection and refraction. So let's dive right in and follow a single ray of light to see how these simple rules create the entire world we see. Okay, so before light can bounce or bend, we have to understand its most basic default behavior. And it turns out light is surprisingly simple and incredibly predictable. That's it. Rule number one: light travels in a perfectly straight line. Think about a flashlight beam cutting through the dark, or a really sharp shadow on the ground. That all happens for one reason: light doesn't curve. This is our starting point, our baseline for everything else. So what happens when our straight traveling ray of light slams into something it can't pass through? Well, it bounces. And that bounce is what we call reflection.
Now, here's the really cool part. That bounce isn't random. Not at all. Whether that light hits a super smooth mirror or a rough piece of paper, it follows a very precise, unbreakable rule.
Think about a pool ball hitting the side of the table. It bounces off at the exact same angle it came in at, right? Light does the exact same thing. This one single beautiful law governs every single reflection you've ever seen, from your own face in the mirror to the moonlight shimmering on a lake. Okay, that's all well and good for a flat surface. But what happens if that rule, that perfect bounce, applies to a surface that isn't flat? This is where things get really fun. Just look at a spoon. Its curves change everything. That simple spoon shows you the two main types of mirrors perfectly. A concave mirror, that's the inside of the spoon, curves inward. It focuses light, which can make things look way bigger or even flip them upside down. But the back of the spoon, that's a convex mirror. It curves outward, spreading the light out, which always gives you a smaller, upright image. And this is exactly why they're so incredibly useful in technology. Your car's headlights? They use a concave mirror behind the bulb to take all that light and shoot it forward in a powerful, focused beam. And that side view mirror that says objects in mirror are closer than they appear? That's a convex mirror, giving you that wide view of the road by making everything look a little smaller.
All right, we've nailed down what happens when light bounces. But what if it doesn't bounce? What if it can actually pass through an object, like from the air into a glass of water?
You'd think it would just keep going in a perfectly straight line, wouldn't you? But it doesn't. Its path actually bends. We call this refraction, and it is the entire secret behind why that straw in your drink looks like it's broken right where it hits the water. And the reason it bends is just amazing. It's because light travels at different speeds in different things. It goes fastest in a vacuum, a tiny bit slower in air, and even slower in water or glass. Imagine you're driving a car from smooth pavement onto a big patch of thick mud, but at an angle. The first wheel that hits the mud slows down instantly, right? And that yanks the whole car into a turn. That is exactly what happens to a ray of light. And get this, the direction of that bend is completely predictable. When light slows down, like when it goes from air into glass, it bends inward. When it speeds back up, going from that glass back into the air, it bends outward again. It's a consistent, predictable shift every single time. So if we know light is going to bend when it goes through different materials, how can we actually control that bend? Well, by very carefully shaping the material itself. And that's all a lens is. It's a tool for harnessing the bend. And just like with mirrors, we've got two main flavors: A convex lens, the kind that's thicker in the middle, it brings parallel light rays together or converges them to a single point. That's how a magnifying glass works. Then you have a concave lens, which is thinner in the middle. It does the opposite. It makes light rays spread out or diverge, which is super useful for correcting things like nearsightedness. Now, we actually have a way to measure this bending power. It's a unit called a diopter. You can just think of it as a rating for how powerful the lens is. A bigger diopter number just means a stronger lens, one that can bend light much more dramatically to get things into focus.
Okay, so here's the thing. These ideas, reflection and refraction, they're not just something you'd find in a physics textbook. They are, quite literally, how we engineer sight itself, both in our own amazing eyes and in all the tools we've built to see the world better.
I mean, just think about your last eye exam. That whole process is a masterclass in refraction. The optician is just putting a series of lenses in front of your eye, each with its own specific power, looking for the perfect combination that will bend the light just right so it focuses perfectly on your retina. And the math behind it all? It's almost shockingly simple. The powers of the lenses just add up. If you put a +2 diopter lens together with a +0.25 lens, you get a single lens with a power of +2.25. It's that simple addition that allows us to design and build everything from tiny camera lenses to gigantic telescopes. And that's our journey. We started with a simple ray of light just trying to go in a straight line. We watched it bounce and bend according to these beautiful, predictable laws to create every single image we see. And it leaves us with one last big thought. If everything we see is just light being bent by the lens in our eye, how much of what we call reality is really just a trick of the light?